All right, we've been looking at these ring flip equilibrium problems where we've got some stable conformer and it's in equilibrium with the unstable conformer, and there's some equilibrium constant that describes the ratio of the unstable to the stable concentrations. Usually we're after the percent abundance of the stable conformer. So in order to solve that, we have to build an ice table where we have some initial starting concentration of the stable conformer and 0 of the unstable. We have a change, which is minus x and plus x, and we have final concentrations of C0 minus x and x. So then we can express the equilibrium constant in terms of this progress variable x, which is just x divided by C0 minus x. Now, we're not usually after what the absolute concentration is, we're after what the relative concentration is. And the percent of the stable conformer is just its concentration, C0 minus x, over the initial concentration, C0. So I need to solve this equation for x, and I can do that with a little bit of algebra. I can multiply both sides by C0 minus x. And then I can distribute k. And then I can group my like terms. And then I can factor out my x. And then I get k plus 1 times x. And then finally solve for x. All right, so this we can plug in up here to our equation for the percent of the stable isomer. So the percent stable, and there's also a times 100 here because we're going for percent, not fractional abundance. So the percent stable is going to be C0 minus K C0 over k plus 1 all over C0, and then I'm going to multiply by 100. Now notice that C0, the initial concentration, is in both terms in the numerator, and it's in the denominator. So if I factor out C0 from the numerator, it will cancel with the thing in the denominator, leaving me with 1 minus k over k plus 1, all of that, times 100%. And so I can express the percent of the stable conformer just in terms of the equilibrium constant k, and this initial concentration sort of vanishes because it doesn't matter for equilibrium problems where you're looking at a stable to an unstable conformational isomers.